welcome, welcome. We are early, but let's see who's presenting first. The desalination team. Okay. Is the desalination team online?
Yes, I am here.
Okay,
okay. Cedric and everybody will also be.
Okay, yeah, that's fine. We're a little early, but I want to avoid what happened last time when we went quite a bit over time, so that's okay. Does anyone have any questions about the midterm?
Yeah. Is there anything that we should be studying or anything?
You should be studying everything you've learned until the week of the midterm.
Okay. I mean, is there any like guide or problems we should be doing?
Yes. So there are a few example problems that are posted, particularly on the geometrical optics slides.
Okay.
You should definitely do those. They're on the website and on Canvas.
Okay.
The exam is on October 15th, right? And it's going to be a timed online exam?
Actually, it won't be timed. I think it will be 24 hours. I haven't quite decided exactly how much time, but something like that. So it's not going to be in class, but we won't have a class lecture that day. But we'll talk more about it on Thursday. So in the interest of time, let's see. Okay, we have what? Okay, we are 12:25, so we should probably start. Is your team here, Prate?
Yeah, I think we're all here.
Yep, looks like we're all here, and I'll be the one sharing the screen. So.
Okay, is that Cedric? Okay,
yep.
Okay, Cedric. I'm gonna. Okay, welcome everyone. We are here on assignment 3. So I think you all know what to do. One quick point I wanted to make is I will post the instructions for the next assignment later this week. And from the schedule, you know that is November 3rd. So you have roughly a month for it, but it's a bit more involved in terms of what you need to do. So just keep that in mind. And we'll talk briefly about this on Thursday. So, okay, Cedric, I see you're sharing and I am going to go on mute. So the floor is yours.
Okay. Thank you very much. Can everyone hear me? Okay,
yeah,
so
you're good.
Okay, great. Okay, great.
It's good.
So our team is the photon filter team. We are the solar desalination project, and this is our presentation on our innovation. So with that, I'll jump into the problems with the existing methods. So the main problem is conventional desalination is very energy intensive, consuming 10,000 tons of oil every year, which contributes heavily to climate change. The alternative to conventional desalination is renewable energy desalination, but the problem with that is it's mainly low yield, producing small quantities of fresh water, and is not really scalable to like a production plant type of design. And additionally, it requires a large area. And the problem that is common between these two methods is that they discharge brine, which is highly salty water. This is harmful to the marine life where the brine is discharged into. So there's really this trade-off between conventional methods, which are large-scale, high-yield, but energy-intensive and expensive, and renewable methods, which are simple and generally inexpensive, but produce low quantities of fresh water. So we went into a brainstorming, and the first conclusion that we came to is that conventional methods are really well developed and have lots of engineering analysis have been invested to improve this technology existing. And so we didn't really feel like that was an area that we could significantly improve in a short amount of time. So we went and looked at other questions. So how can we address the brine discharge? Well, we thought about maybe we could extract salt from the brine, which would have two effects. First, it would reduce the concentration of the brine, reducing the effect to marine life. It could also provide salt, which is a useful product. And we found that solar salt desalinization is actually a relatively complex process because you cannot just evaporate all the water and use the remaining salt, because there's also other inclusions in the salt water that can be potentially harmful to human health. So we went and looked at solar stills. We found that solar stills really provide opportunities to mesh with many other technologies to improve their performance, namely like water additives, using heat storage, using reflectors, improving condensing efficiency, using wicking materials and insulation, among a couple other methods. So we found that really solar stills offer many potential technology synthesis possibilities to improve their yield amount, which is the main problem with renewable energy desalinization. And so we looked at how can we increase the yield of solar stills, and we can do that in two main ways. And the first is to increase evaporation. And so we can really increase evaporation by using a wicking material to increase the area of evaporation. We found that the water depth is really an important factor because typically the heat is absorbed in the bottom surface of the water, whereas the evaporation happens on the top surface. So typically you want a very thin layer of water. And then we looked at how can we lower the water evaporation temperature. So if we can maintain a constant temperature, but have a lower evaporation temperature, we can have more evaporation. And so one way you can do that is using a vacuum system. And I'll leave that for later on in our slides to talk about more. And then the second way is really to increase the condensation. So increasing condensation, we found that a big metric here is the difference between the water temperature and the condensing temperature. So you can have a big temperature gradient there, then you can have more condensation forming. And so we wanted to cool the condensing surface, and this really led me to think about a paper that I read a couple of years ago about a passive radiative cooler. And what this is basically glass nanobeads sandwiched between two layers of plastic. And how this works is it lets the solar radiance pass while emitting in the infrared range, which is the atmospheric transmission band. So this material basically radiates directly into space, which can then cool any surface that you place this material on without using any input power. And so then with that, I will pass it over to Joseph to talk about our potential innovation.
Cool. So as Cedric stated, the method that we're using to kind of drive our innovation is solar stills. The operation principle behind solar stills is basically you have a blackened basin filled with saline water, which is then heated, causing evaporation on the inclined plane. The covered plane then condenses, and then fresh water is then deposited back into the basin. Some advantage of this, as Cedric mentioned, is it's simple, readily available materials, eco-friendly, and it's low maintenance and cost. Some of the disadvantages that we are trying to focus our innovation on is the low yield and the low efficiency of the solar still. Go to the next slide. So solar still is affected by several different parameters, some controllable, some not. Obviously, the first being environmental, which is not easily controllable just because you have wind velocity, solar radiation, ambient temperature, and all those kinds of things. Some of the things that are easily controllable of the solar still is the design. You can control the water depth, the evaporation area, the condensing cover angles, and you can easily control the operation of the entire system, the water feeding system, the position of the solar still. Those types of things are easily controllable. So to kind of go back to our disadvantages of the vacuum, of the solar still, we decided to implement a natural vacuum. And what a natural vacuum does is it creates kind of like a vacuum inside of the still to decrease the saturation temperature of the water and the saline water. So the advantage of this is you can reuse some of the seawater and the waste can be reduced, but a disadvantage of this comes where the saline water must be maintained at a higher temperature than the fresh water. So that is kind of where we are going to further our innovation to try to produce better results in that area. We found a preliminary, on the next slide, found a preliminary kind of design setup that we found in another paper that basically consists of a glass cover and a basin. It's equipped with a reflecting mirror and an insulator inside. There's a natural vacuum inside of it, which kind of to decrease the saturation temperature of the water and to increase the yield. Obviously, it's not shown in this picture, but the feed water in the basin is heated by solar energy, which is then evaporated and condensed by the inner glass cover. This is kind of just like a simple schematic that you guys can visualize. I'll then hand it over to Pratay to kind of go over the theoretical advantages.
So as Joseph explained that natural vacuum, vacuum produces by means of gravity can create vacuum. So what it means is that it reduces the pressure on top of the liquid or the confined system. So it has been experimentally shown that natural vacuum can reduce the pressure up to 7 kilopascal or even more depending on the ambient temperature. So what it does is that, for comparison, let us think that in a free system surrounding us, the pressure is about 101 kilopascal. So natural vacuum significantly reduces that pressure, and what it does is that it reduces the boiling point, because as the pressure reduces, the boiling point of the water should reduce, and which in turn would increase more vapor. So this relationship is described in the Clausius-Clapeyron relation, which is materialized into this equation, where P1 is the pressure at which the boiling point temperature T1 is known, and P2 is the pressure at which boiling point T2 has to be calculated, and R is the ideal gas constant, and HV is the heat of vaporization, which for liquid water is about 40.66 kilojoules per mole. Now, if we employ all these values into this equation, we can come down to T2, which is only unknown, and calculate it as to be 309 Kelvin or 36.85 degrees Celsius. Now, for comparison, if we had a ambient pressure of 101 kilopascal, we would have a boiling point of 100 degrees Celsius. So if we include the natural vacuum into the solar still, we can reduce the boiling point of the temperature quite significantly, which in turn would produce more water vapor, and that should increase the water production capacity of the solar still, which has been a big problem with the solar still thing. Now, this is all a logical flow of conclusion. If we move on to a more detailed view of the hourly yield of a conventional solar still and our new proposed system, we would have more insights. So the hourly yield of a conventional solar still is basically given by this equation, which is basically developed as a part of a mathematical and analytical model of any conventional solar system, and also has been verified by a couple of experimental processes and solar stills from Nigeria and the African region. So here M is the evaporation rate, which is basically defined as the amount of water being evaporated from the feed saline water and being condensed at the condenser. And H is the evaporation coefficient, which basically depends on the condenser surface, the efficiency, the heat loss of the system, the entropy of the system, basically a complex thermodynamic parameter, which can be calculated experimentally and as well as theoretically to be 7.4. T is the temperature of the water and the condenser, and L is the latent heat of vaporization. Now plug all those values into here, leads to the evaporation rate to be 0.05 kilogram per meter square in 1 hour, which also kind of matches with the African region production rate of a conventional solar still. Now, if we employ natural vacuum into the solar system, the hourly production rate would change into this equation, because it is a combination of a different process of physics. It needs to include the vacuum and everything. So here the AM is the mass accretion factor, which is an experimental value incorporated by Newton for like evaporation happening in vacuum. F is the correction factor, which basically replaces the gap between evaporation in vacuum theoretically calculated and experimentally seen. And P is the vapor pressure at those given temperatures of water and the condenser. Now moving on to the next slide, if we employ those values and assume a correction factor of 1 for simplicity, and we can find the vapor pressures at those temperatures by looking at a chart of water vapor pressures at different temperatures. The hourly yield of the natural vacuum system would be 0.9 kg per meter square in 1 hour. So what it does is that what I'm trying to say is that the vacuum, incorporating vacuum into the solar steel compared to conventional solar steel increases the hourly production rate of 19 times, which is a significant increase. Of course, theoretically, the practical would be a little different, and which should increase, we should produce enough amount of water to reduce the cost per meter cube of water production at a very low capital investment. Now moving on to the next slide, to sum things up, what solar steel does, we have seen, is that it avoids energy intensive desalination process, and but it still has a very low production rate of water, but it's a straightforward and simple process, so it can be synthesized with other technologies to improve performance. Now, if we include natural vacuum into the solar steel, it provides significant performance enhancement in terms of water production rate, and on an application basis, it can be a part of rooftop array system. If we can apply it as a rooftop into villages and into cities, and like integrate it all throughout that small part. But it also needs to maintain water, like the produced water at a lower temperature than the saline water, and that can also be addressed as employing a passive radiative cooler. The other improvement technologies that can be employed is like sidewall wicking material, reflectors, and controlled saline water depth. To sum it up, what we have seen is that by employing natural vacuum, we can increase the amount of water being produced in the solar steel, as well as reducing the cost per meter cube of water product at a very low capital investment. Thank you. This is the references. So if you have any questions, we'll be happy to answer.
Yeah, first of all, let me comment you on a very nice job. So that was very well done, and on time as well. I have lots of questions, but we probably don't have enough time. But one quick question: I didn't completely understand where you're getting the natural vacuum from, and you didn't talk about the power requirements of that. And I know you didn't have enough time, so maybe you can just clarify that in this picture. Yes, exactly. Whoever, any one of you.
So the natural vacuum is a little different than like typical vacuum systems use a pump to create the vacuum pressure.
Yeah. Mm-hmm.
A natural vacuum system can basically, you fill the saline water tank, and then you have it up elevated at a high place, and by letting the water fall down, you can create a vacuum in the surface or in the area above the water. And so by letting the water fall about 10 meters, you can create a large vacuum, which will reduce that evaporation temperature. So you don't have to have any power. You just have to basically fill the top and then open a valve somewhere, in this area to allow the water to fall. And that naturally creates the vacuum, hence the name natural vacuum.
How do you ensure that the air doesn't diffuse through the water and enter the vacuum? It's not a perfect seal, but I guess you don't need like a very high vacuum. So I think I understand what you mean.
Yeah, you don't create a perfect vacuum, obviously. And the other problem is that you have to separate these, the product water and the saline water. Mm-hmm. Typically that's done with a fan, so that would have to typically be powered maybe by a solar PV.
Yeah.
And the final issue is that really the product water, because it doesn't have salt in it, evaporates at a lower temperature, because the salt increases the evaporation temperature. So you actually have to hold the product water at a lower temperature so that you don't have backwards evaporation.
Got it. Yeah.
And that's one thing that we could address. People have addressed that in the past by putting that in the shaded region so it doesn't absorb solar radiation. And obviously we would do that as well. But you could put it, that passive radiative cooler on it to increase the temperature difference between those two bodies of water.
Fantastic. Yeah. I understand. Yeah, I think I got the gist of the idea. One interesting concept. When you were talking about this, I really like, by the way, I'm familiar with the space coolers, the films you showed. I wonder if there are ways to turn these this concept into like a roll-to-roll approach. Like, is there a way to roll up, instead of having these big bulky reservoirs, could you have like a sheet reservoir? Because the still itself is flat. It's just a reservoir that's bulky. So I wonder if you could somehow, which increases the surface area of the water. But anyway, just a crazy idea to think about. Because if you could roll it up, then the cost of production, cost of deployment, all this goes down dramatically. But I'm
so
not sure.
this paper here that actually built this passive radiative cooler found a way to kind of mass produce it, at least in sheets. And you can see here these people's hands, they produced quite a large area of it.
Yeah.
It would be interesting to have it like more the feed water or the product water spread out, so you have a thin layer of product water, so you get more cooling effect. But you'd also have to have more area to hold that water in. But I don't know if that would be an issue. It's something we could consider for sure. It's a good idea.
I mean, there's a way to perhaps eliminate the water tanks out of it, but then it would create a problem of like pumping the water back into the system and so on. But we can definitely look into that.
Yeah. Well, I was thinking, there are these water bottles that can be rolled up, right? And they're flat, you put in your backpack and you fill it up. So I wonder if there's some clever way to incorporate that into the design.
We'll look into that.
Okay, great. Thank you. And let's move on to the next team. So let's see. Photovoltaics team, who is going to share?
I will share.
Okay. Go ahead. And
okay. Can you guys see it?
yeah, perfect.
Oh, perfect. Okay, cool.
You're on. Go ahead.
You ready, guys?
Ready.
Yeah. Well, hey everyone, we are Team Solarad. Today we're going to be talking about some of the ideas that we brainstormed for photovoltaics, and ultimately we decided to pursue the idea of solar shade. So we need to address some of the problems associated with photovoltaics. There's, first of all, a high cost. Even though we've seen the cost of solar panels go down, there's still a significant cost for installation, like materials, as well as the size. Not everyone is going to have enough real estate to actually install this due to the metal frame and the amount of panels needed to provide enough usable energy. And then efficiency, a lot of current solar cells are only getting efficiencies around 17%. And this becomes an even bigger issue when it's cloudy or you have unideal weather conditions. So to solve this, we came up with a couple ideas: solar drones, solar driveway, sunflower helper, cloud city, and solar shade. So we first looked at existing solar drones to get a better idea. Some big companies like Facebook and Google basically wanted to build this airplane-like UAV to provide 5G internet coverage, high bandwidth over like high altitudes. But a lot of these projects got canceled and didn't meet design requirements. Google actually ditched their Solera and went with the loom on the far right to make this happen. So instead of doing something that's like 180 feet in diameter, we wanted to scale it down. So our next slide, we're gonna have Wi-Fi, which is gonna be a Wi-Fi hotspot drone. So it'd be really cool to have a solar panel on it while it flies so it can charge at the same time. And then it'll also have a solar powered landing mat that'll also have battery attached in case the weather is unseemly. And so it'll work on cloudy days. And sorry, if you could go back, it would also be able to carry supplies within a certain weight limit, which could potentially work for like medical purposes and things of that nature. Our next idea was the sunflower helper. So it was going to have microcontrollers to make it self-adjusting, so it can always find the maximum amount of sunlight no matter the angle. And it's customizable. You can use it for whatever you want, whether it's your car, your sprinklers, whatever you have outside. And then stemming off of the solar roads, we thought of solar driveways. which would be really cool to have in Utah since it might be useful for de-icing or melting all the snow on your driveway. And it would just look really cool. But it is expensive and it might be inefficient since your house is going to cast a shadow on it for several hours out of the day. And we did some quick calculations to see how quickly it would be able to melt the snow, and it didn't seem really feasible. So our fourth idea was Cloud City. This is actually a Star Wars picture, but the idea was an aerial solar farm that's going to float above the clouds so that you're not getting any interference from nature, wildlife. You're going to get the maximum sunlight absorption, but it is a challenge to get the solar system up that high and maintaining that height without depleting all the energy you're getting. So our final idea, I'm going to let Vo present on solar shade.
Yeah, so with solar shade, it's essentially an awning that has a solar array on top of it. So it provides shade for the user while collecting solar energy. The innovation comes into play with the solar array itself. So some of the innovations include a thin film, flexible bifacial solar cell that allows us to harvest energy on both sides of the material, hence shrinking down the size as well as increasing the efficiency. And so combining this bifacial solar cell with holographic tuning, which are these films that will tune out any wavelengths that can't be harvested by the solar cell, for example, infrared, and let that pass through and allow only wavelengths that can be caught by the solar cell to reflect back onto the solar cell. And then including electrowetting with somewhat a solar tracker. It is essentially a hydrophobic layer that sits on top of the solar cell that you can have these tiny little water beadlets that when a voltage is applied, then it changes the shape of that water beadlet, essentially changing the angle of these water droplets like a lens and directing the sunlight directly onto the solar cell wherever the sun is. And then, as I mentioned before, it allows infrared to pass through. And so as the infrared passes through, a heating source would then absorb this heat, and a thin film thermal harvester would harvest this heat energy and convert it to solar energy or usable energy, additional solar energy for the user. And here's Yo-Yo to talk about why we picked this idea and any challenges we may see with this idea.
So the reason why we picked this is because it's a high efficiency, low cost, and small size. It can maximize quantity of energy while maintaining a minuscule size. It tunes the solar light onto both sides of each cell. It keeps solar cell operating at 1 year at their peak performance temperature, which normal solar panel will not be able to achieve. It refracts infrared light away from cells and harvests that thermal energy. With the use of less solar material and no need for metal frames, the cost of material and installation is reduced significantly. Besides that, with the ability to be able to fold up itself, it is not only more visually appealing, but also provide the user with the shade when needed without taking up so much space. And the reason why it hasn't been tempted before is because each individual innovation is fairly new, and a combination of these innovations has not been utilized yet. However, we can still see issues that may come up with folding ability of awning solar array and its durability, and maybe also the durability of the electrowetting layer underneath the thermal load. And Nick will explain the preliminary analysis for us.
Okay, so for preliminary analysis, we used a single-family home in California as our model. Year-round, they get an average of 5.82 hours of peak sunlight.
Did he freeze for anyone else?
Yes, he's frozen.
Yeah, he is frozen.
Hey, Nick, I think you are frozen. Fo, will you maybe be able to just catch up with kind of like Nick was left behind?
Okay, so I'll just take over now.
Mm-hmm.
So for our preliminary analysis, we just took a average single family home in California. First, we had to gather some information. So year round, California receives about 5.82 hours of peak sunlight per day, and an average family consumes about 547 kilowatt hours per month. So with this in mind, got some information for an average rooftop solar array. So for about a 5 kilowatt system, that requires about 23 60 cell monofacial solar panels. And on average, each 60 cell monoface solar panel is about 1.62 meters squared and produces about 275 to 285 watts per panel. So with this in mind, an average rooftop solar array for this size for a single family, it would take about 37.4 meters squared of space. And an average cost of installation would be about $13,000 to $17,000. So with our product though, so a bifacial solar panel that utilizes holographic film can produce approximately the same amount of wattage as a monoface panel at 1/3 the solar panel material. So hence significantly lowering the cost, because that's where the cost is heavily in the solar panel material. Hence, then our solar panel would be about 1.13 meters squared of film and then 0.57 meters squared of bifacial solar cells. So with this in mind, we think we need approximately 23 of these. Sorry, we had to update our numbers, so I guess it didn't come through. With solar panels with biface with HTC, for a total area of approximately the same 37.4 meters squared, but however, only about 12.5 of that would be solar material. So then we not only decreasing costs, but as well as since it's able to fold up, it takes up less space essentially. Adding the electrowetting layer on top of that would only increase efficiency as the solar panel will get direct sunlight, as well as we would get additional power that is generated from the thermal harvester. So in conclusion, we believe with our novel idea, it stands to be a good alternative to your average rooftop solar array for residential and commercial use. And due to its higher efficiency, space-saving abilities, and cost-effective materials and installation, we believe that solar shade will provide users allow users to go green without sweating a drop. Thank you. Any questions?
Very good. I have to say, you had the most creative ideas so far, so that this is very exciting to see. So I really liked all the different ideas. I did have a couple of quick questions. Sorry, let me look at my comments first. So I like the idea of the drone with the Wi-Fi. This is actually quite interesting because it might have, and no problem, Nick, understand, we have all have to be a little more cooperative. My kids are on Wi-Fi too, so I completely understand if your internet doesn't work. And your teammates took over, so that's really good. So that shows that you guys are working together as a team, so that's good. The Wi-Fi that you were talking about has some interesting applications potentially for emergencies. So it's kind of an interesting idea because, you know, if you think of Hurricane Katrina, for example, right? So if that happened today, you know, if we want to, you know, Wi-Fi access is now very important for schools and all kinds of things. So that might be an interesting thing. So that was one quick comment. And I also, the first thought that came when you showed the Star Wars image was that potentially one could use big balloons to hold up the panels, and they could be very thin films. But again, crazy ideas, but very interesting. And definitely the one you picked is more practical, but also has lots of very interesting innovations there. I suppose in the interest of time, I only have one quick question. Can you explain the reason for choosing a bifacial cell as opposed to like a flexible thin film cell? Is it because you want to make different shapes, architectural shapes of the awning, and make sure that you can collect light from all directions?
Yeah, so that's part of the reason, due to not all houses are made the same. So it would require different shapes for different awnings for different houses. But it was just to not only increase efficiency, just to capture the backside as well. But then,
but if it's an awning, let's say the backside means you're facing the earth, right? Facing the people underneath.
yes, so that's where we would have a white material in the bottom to optimally reflect any light that passes through back to the solar cell. But any infrared energy would be collected by this white material, and that's where the thermal harvester comes into play. As well as with thermal harvester, there's a cold plate and a hot plate. And so the cold plate would be facing the user, so it kind of be creating a cooling effect under the awning.
Got it. Okay. Yeah. Interesting. Yeah. So I suppose you could think about it in levels of complexity also. I mean, you could start with the simplest possible thing, which is just the awning, and then you can add on the electrowetting idea to improve tracking, add on the thermal harvester to improve production and things like that. But all of those could be like an add-on kind of thing.
Yes.
Yeah, very, very interesting. Great. Oh, I forgot. Let me make sure I run the poll. Hold on before I forget. And you guys were on time, so that was fantastic. And anyone else, feel free to ask questions as well. So, and while the poll's happening, I should mention, I think I've said this before, for assignment 4, you are welcome to experiment or even make like a simple model and so on. You don't have to, but I mean, if you are so inclined, that's always a good thing to do. Okay, a couple more people and.
Hey, Professor, can I do a quick comment?
Sure, go ahead.
I think that's great. Our group, we're 090. We're also doing solar panels.
Yeah, and you're all on Slack, so you can always compare notes there.
Yeah, this is great what this group is showing. I just think that's I thank you very much for showing the origami or like the drones that we didn't explore that much. That's great stuff. So thank you.
Yeah, very cool. Okay, great. Let's thank you again, and let's have the next team, the daylighting team, who's going to share.
I'll be sharing.
Dan, okay, perfect. Go ahead. I have to say, this is one of my favorite parts of the class. Really hearing all the fun, exciting, interesting ideas. So thank you for doing all your hard work.
Okay, can you guys see it?
Yep, perfect.
Okay.
You're on.
Cool. I think Way's gonna get us started.
Okay. So my team will talk about daylighting. So our team name is Shining Light, and these are my team members. So can I go to next slide? Okay, the contents. So we are going to cover the following 4 parts: streaming problems, our brainstorming and the solution to a problem, and some basic analysis. Next slide. So the first problem we are facing is the heat. We all know the sun is the hot and powerful light source. The sunlight can penetrate through the glass window and produce a huge amount of heat. So it will have significant impacts on the building's HVAC system. And the second problem we are facing is the glare. And the direct sunlight penetrates into the inside spaces, often produce a very unpleasant glare on the work surface. So it makes it very difficult for us to work, especially when we are using our computer. So it's tough for us to view the computer screen. In the next slide. So the third problem is very tricky because the sunlight is hard to control. You can control the modern electrical lights through a switch, but the sun operates outside the building, so it is out of our control. It changes through the day, it changes with the weather, and it changes from season to season. So next slide. Okay, so this slide is about the brainstorming, and my team members will talk about this slide to address the problems I just talked.
All right, so I'll take over from here. Can you guys hear me?
Mm-hmm.
Cool. So I'll actually be handling most of the rest of the presentation. Sky's feeling a little ill and their throats just wrecked. So I'll do the talking this time. So a lot of our brainstorming, we're focused on, these three issues, and we were looking at sort of different approaches to each one of these problems. For heat, there's things like transitional films that adapt sunlight intensity. There are UV films you can put on windows that are already readily available on the market that also reduce heat considerable amounts. We also toyed with the idea of finding a way to capture the heat using heat generators, thermoelectric materials, and using it in some way rather than just trying to sort of get rid of it at the window pane level. As far as glare, we were toying with ideas to use some sort of blade window configuration, essentially like a type of motorized system that could slightly adjust windows, things like that to adjust it. Turned out to be kind of a logistical nightmare, so we didn't spend too much time working on this one. There's also the use of anti-glare coatings that can be used on walls. Different materials and different even paint tones can affect things like that as well. There's also just the logistical approach of setting up a work area in a space to reduce glare. As far as dealing with the dynamic source that is the sun, a lot of the things we were looking at are going to be pretty typical along throughout a lot of other presentations I'm sure we'll see, where we want to be able to capture energy even though the sun is moving throughout the day, throughout the year. So some of our approaches to that were things like using a GPS system. We could use photocells to actively monitor the light and adjust accordingly. There are ways to use systems of reflectors, like the thing that Dr. Manon posted in the chat this morning. There are systems like that. We showed a system called Solitube in our last presentation that uses a type of lens that can gather light readily from a lot of different angles. Oh, okay, so we decided to start going into major components that we thought would really assist us in creating daylighting systems that would be applicable in a wide variety of situations. One of the first things we decided would be pretty necessary is a light sensor, a photocell. These things, as many of you already know, they can sort of take visible light as an input, convert it to an electrical signal, and send data saying that, hey, we're receiving this amount of light. Photocells are actually pretty commonly used in Utah, especially in a lot of building code. Any daylit area, you have to have photocells that will shut off lights within a certain distance from windows. So these are already readily used. It would be easy to adjust them and use them in slightly different systems. So that was kind of our a no-brainer component to be using. The other thing we decided to use as well is reflection. We didn't want to worry about just we didn't want to have have it be left completely to sort of the fates as far as how much light we would be getting. So we wanted to use some sort of method to control the light. And of course, reflective panels are going to be an easy way to do that. We also looked at some other technologies that could be useful as far as managing daylighting. Things such as privacy glass, which is a system where you flip a switch and it runs an electrical current through these panes of glass and rearranges certain molecules in the glass. I apologize, I can't remember the exact material. But when an electrical current goes through these panes of glass, it actually realigns the molecules into a crystalline structure and diffuses light pretty aggressively, as you can see in the off picture. That's when those structures are aligned. We also looked at sort of simple notions of having sort of dynamic shading systems that are just powered by motors, things like that as well. There was another technology that we looked into, which is really very interesting. What they do is these devices essentially gather a bunch of sunlight, and using fiber optics, they actually transmit the light directly through these cables into different spaces, as you can see in this image down here. In the bottom right, they've got the collectors on top and systems of cables that go to different rooms. I looked into this technology. I looked into the pricing a lot, especially because that was one of the things where, because it's an existing technology, I wanted to see what kind of limitation that was. And they can get pretty expensive, these types of systems. So this collecting system that we have an image of is one of the larger ones. I couldn't find a good picture of their smaller ones, but they start at about $500 for the smaller collectors and then start to go up for that. Every foot of cable is going to be also about $10. So $10 per foot. And then you can only use it so far. It's only a couple hundred feet at most that this light can be transmitted. So what we eventually settled on doing was just using the simple concept of light shelves and adjusting these. Now these are just flat panels that are placed, as you can see in that bottom left image, they're placed in a space above eye level, of course, but what they do is they simply act as the first part of a two-part system of reflectors. Very simple. You have sunlight come in, the incident rays strike the top of the shelf, and then reflect off of that onto the ceiling, which is then diffused throughout the area. These are very nice because especially if you just have them static, like here, they're fairly inexpensive and you get a lot of great light, which means you're going to have energy savings and things like that. Depending on how the panel is angled, you can have sunlight actually dispersed throughout a pretty wide area. There are some disadvantages. It does require a flat, lightly painted ceiling to be most effective, which kind of butts heads with a lot of construction, sort of the construction, I don't know, paradigm at the moment. What I mean by that is there's a lot of open ceiling construction that's being done. Most new spaces that you see like to incorporate this, at least at the moment. It's actually starting to, that style, I guess, is starting to go out of vogue, I guess. But that is pretty common with a lot of newer constructions to have those open ceilings. The other issue is that, of course, if we have these static shelves, they work best at a certain time of day during a certain time of the year, and that's entirely it. So what we wanted to do was we wanted to adjust this existing system. We propose integrating a system of photosensors and motors and rotators that can detect the amount of light coming in. And ideally, this will probably involve photosensors both on the panels themselves as well as the ceiling that can sort of coordinate with each other to make sure that regardless of where the rays from the sun are hitting, they will be able to be utilized. So this will involve perhaps motors moving up and down, as well as being able to rotate to make better use of the rays there. So, and if you'll actually see in the rotation mode, if we had put this panel, rotated it in the other direction, you know, we could have light shooting out further into spaces as well. So there's a lot of adaptability that comes just with being able to have an automated system to move these things as well. So that is our preliminary analysis. Of course, there's going to be things like manual overrides as well. But it's the biggest sort of boon with this kind of system is that you'll have an automated network of photosensors communicating with each other, letting each other know what levels of light they're getting, and then adjust accordingly automatically without having to have any sort of user input. So we'll open it up to questions there. I apologize, I did actually go a little bit over time.
That's okay. Really, really good. Yeah, I'm also very excited to see all the solutions here. So a couple of quick comments and questions. One thing which is very important for daylighting is the color of the light. So, you know, and we'll talk a little bit about this later in the class. So in other words, you know, there's certain spectrum of the light that makes your product, you know, you feel better, right? Which we know from, you know, the seasonal depression rates go up in the winter, for example. It's some of this has to do with loss of sunlight, but also some of it has to do with the spectrum. So that's a good point to keep in mind, like, are you going to modify the spectrum of sunlight when you do the daylighting? So just a quick comment to keep an eye on. And I really liked when you talked about the photocells. So if you actually had multiple photocells, because they're spaced apart, you could do some sort of a triangulation algorithm, kind of figure out where the sunlight is, which is, I suppose, in an indirect way what you're doing with the networked system that you were describing at the end. But that's an interesting approach, for instance, to maybe some of the other teams when they want to track the sun. I was thinking in particular of the electrowetting part, but anyway.
Yeah, the thinking there was...
Yes. Yeah,
oh, sorry to interrupt. The thinking there was primarily just
no, go ahead.
It would be pretty easy to both, because these devices are readily available and fairly cheap, have one installed both on the panel and on a location on the ceiling in the adjacent room, specifically where we're going to want the light focused the most. You know, because we can look at a space and determine, you know, where we want this to hit. So it'll also, there would be some, it would be necessary to have some sort of, you'd want to think about this pretty early on, because installation would vary greatly by spaces. But yeah, that's
which by the way brings me a very important point for all the teams. Your customer who's, you know, will really drive the technology. For instance, Dan's here talking about new construction, but the vast majority of your customers may be retrofitting, and that will really drive the design and technology of what you pick. So this is a very, very important point. By the way, I do have one potential solution to your your problem of the open ceiling, because of course we all like the open ceiling layout. One idea would be, could you make your light shelf transmissive? And instead of, you know, just letting it transmit directly, maybe there's some clever ways you can actually diffuse the light in. And that's clearly an optical design.
Yeah, that could be. And
Did you get that? Okay.
I was thinking, it's something that I was kind of thinking about, but didn't really have time to look into deeply. But if there was sort of like a wedge-shaped diffuser, you know, kind of thing that could bring in light and then diffuse it more evenly in a space. I don't know if that would be able to shoot light as far out, but yeah, it was something we started to think about.
Yeah, those are all very important points. And we should stop and move on to the next team. Oh, actually, I need to do the polling. Hold on, keep forgetting. But while we do that, one comment I would make is that if you actually come up with a good innovation, I know for a fact that 3M would be very interested. And I know the folks who do, they have a business unit called the Daylight Redirecting Optics, DRO. And I've been there several times, and some of those pictures you showed is something I've seen in person. So it's definitely very important and potentially a very interesting opportunity. So while we are doing this poll, I'll have the next team, the pasteurization team, take over the screen. Stephen, okay, perfect.
Yeah. Did you see the screen?
A few more people on the poll. I think we're done. Okay, perfect. Let me just close this and I'll start the timer. Hold on 1 second. Okay, you're on, Stephen.
All right, hello everyone. We are the Pure Water Vision team, and our job is to do water pasteurization. Our team members are me, Carl Peterson, Stephen Tran, and Abdullah.
So these are the list of the primary problems with water pasteurization. The first being the cost. Water pasteurization is mainly marketed to impoverished area. So when building a water pasteurizer, a lot of calculations must be conducted on the cost to try to reduce it as much as possible, whether it's initial cost or long-term cost. The second problem is deciding what type of sensors or timer to use. So one type of sensors is shown here on the right, which allows the melting of the fat when the water heats up. While this is really inexpensive, it has been designed for error, so it increased the temperature which is necessary to eliminate the bacteria. So this decreases the efficiency. Although an electrical sensor would be more sensitive to the heat, it would be more accurate, it costs a lot more. So there has to be a compromise in trying to find a sensitive sensor while being inexpensive as well. And a third problem is being energy efficient, trying to find which type of insulation is the best, and trying to keep the heat inside the device so that this speeds up the pasteurization because none of the heat is being lost, which in turn lower the long-term costs, which is another problem because it's able to produce more pasteurized water over time. And next, Abdullah will present some of the solutions to these problems.
Okay, for the solution to long-term cost, we presented to 3 parts: long-lasting material and preheating in bottled water and increased volume of water pasteurization. For lasting material, it's to be reusable insulation and low maintenance. For preheating, speed up water pasteurization and lower energy time needed to heat later. For the volume, expand containment of water to pasteurized, for example, the solar bottle. And for the solution of water temperature sensor timer, we implemented actual sensor timer to higher sensitivity to higher higher accuracy, increase energy efficiency, and decrease room for error. Simple water temperature sensor, it's expensive, first thing, and they can be built by anyone and anytime for the temperature sensor. The solution to energy heat efficiency, the better solution optimize greenhouse effect, glass wool, paper, and good thermal conductive material. Speed up water pasteurization, decreasing tracking sunlight, move the lens from the sun, move, optimize angle for maximum heat at all time, heating of water rarely, rarely slows.
Carl, you're up.
Sorry, I was muted. So what we're going to use is the flow-through pasteurization device. We explained this a little bit in our first presentation, but I'll give a brief kind of explanation again. So first, we're going to start off with the, can you see my cursor? I guess Stevens. So we have our tank, which is our storage, and you pour water into that. It flows through tubing into a heat exchanger, and then into a solar cooker box where it heats the water up to 180 degrees Fahrenheit, pasteurizes the water, and is let through the box via a thermostatic valve back into the heat exchanger, which then heats the incoming water, and then that clean water goes into a clean water reservoir. So why we chose this specific solution is because it's a hands-free device. There's no guesswork to it. So you can literally, the family can just go pour water into it, it filters it, it goes through the device, and it gets output at like a certain rate depending on how much energy is coming in from the sun. So they don't have to touch it. It's completely automated. They can do other things while this is going on. Another reason is it's really good for long-term cost. It has a good, like, it has a high initial cost, but it has a high output of liters per dollar long-term. And the other thing is it's family size. So you can have one of these for a family and just kind of have that for a low maintenance, like 5 years, I think, before you have to change any parts. So a family can just have one of these outside their house and use it for a long time. What has been done, the PAX World Service built a flow-through, but it didn't have a heat exchanger, and also it was slightly inefficient. So it was not really enough for, like, say, an 8-person family or even maybe a 4-person, because minimum you need at least 5 liters per day per person. So it wasn't quite enough for that. So what we're going to improve upon is the PAX World Service flow-through did not have a heat exchanger, and that actually increases the efficiency by, I think, almost 400%. It's pretty significant. Another thing is we can make better insulation, and also we can use a preheating system. So we're thinking of, and the input water tank, we're going to actually use a solar cooker on the preheating. So where he's circling. We're actually going to use an optical solar cooker to preheat the water in the input tank before it even flows into the system to increase efficiency. Another thing is we're going to optimize the size and cost. So all these things cost money. So the thermostatic valve, all the tubing, all the containers cost money. So obviously we need to optimize all of that stuff.
So here is where we do some of the preliminary calculations. These calculations are for the implementation of a preheating system, so a solar cooker at the very beginning. And all these calculations are done there's no heat loss. And these So this first calculation here calculates the time needed to heat a water up from room temperature to the temperature needed to eliminate the bacteria. This is done by finding the energy needed to do that by multiplying the specific heat, the mass of water being heated up, and the change in temperature, and dividing it up by the heating of the solar cooker. or how much watts it can produce. And from research, we found that an average solar cooker has about can produce 56 watts of energy. By doing this, we found that it takes about 4.4 hours to heat up about 3.8 liters of water. So then the second calculation does similar things, but we're trying to find the final temperature of, this is to find the final temperature after it's done preheating. So preheating happens when at the beginning where the water is being filtered. And from research, filtering takes a little bit more, proper filtering takes a little bit more than half an hour. So I put 0.6 hours here. So by assuming that and all the stuff in the previous slide, we found that after the preheating, the water ends up from 20 Celsius to about 27.5 Celsius. So with this, we plug this back in to find our new delta temperature for our second part of the solar cooker, which will properly heat the water up to eliminate the bacteria. This brings the time down to 3.8 hours to heat up 3.8 liters of water. So next we find the efficiency, so the time efficiency. So we reduced the time by 0.6 hours, which is a time efficiency of almost 12%. Next part of the slide shows the calculations for the energy efficiency for the first part with preheating and without preheating. And we found that the energy efficiency improvement was about 14%. And then lastly, we found the cost efficiency. This cost efficiency, so it took about 4.42 hours to heat up the water plus 0.6 hours to do the filtering. With preheating, it took 3.82 hours with 0.6 hours for preheating or for the filtering. And when doing this calculation and accounting for a year, we found that the cost efficiency for a year is with preheating was over 400% more cost efficient. So in conclusion, by implementing something like parallelizing the filtering and adding a preheating, we found that adding an extra initial cost, a small initial cost, would produce higher energy efficiency, cost efficiency, and improve the time efficiency as well. Are there any questions?
Great, nice job. I particularly like the fact that you picked a very specific problem, a solution to the problem. So that's really good because it allowed you to focus. I had a few questions. I didn't understand how the preheating happens. Can you kind of go through that again, very briefly?
Yeah, so Stephen, can you circle the water tank? So when you input water, currently it's just like a little barrel, but the preheating would be to add like a mirror and an optical solar cooker to that barrel. So like we're actually using solar energy to heat the water in just the input storage tank.
So on the left-hand side, that solar cooker is like the main heater. So you could have a parabolic or something. And what you're talking about preheating is kind of like a low temperature, relatively low temperature heating. So you could potentially simply just do like a greenhouse effect, for example. Yeah. Okay. Interesting. And I was curious, Stephen, you mentioned parallelizing. What did you mean by that?
So so like this first part right here, it's not just a reservoir, it's going to be filtering as well. So while like if you put like dirty water in there, it's going to filter out the sediments, and while it's filtering out the sediments, it's also going to be heated up. The water is also going to be heated up as well. So it's doing two things as once instead of one. Okay,
interesting. Have you guys thought, and I understand that you are considering this like at a family scale, but have you considered options of making it modular? Like, could you stack a bunch of these to make it larger? Or
we have considered it. We kind of settled with the family size because like the more components you add, it could potentially create more maintenance and like a larger scale. But that is something to consider, is like a potentially like a village size, but that would be a pretty large system.
Yeah. Got it. What is the, can you explain the efficiency? I know you, Stephen, I think, yeah, you went through a bunch of these. Maybe explain the energy efficiency. Yeah.
So the energy efficiency is just finding the heat energy, which is the specific heat times the mass of water times the delta, change in delta temperatures. So this one calculates the delta temperature for the main solar cooker, which finds the energy from increasing the water from 20 Celsius to 74 Celsius. And then the second one, the second temperature does exactly the same thing, but we're doing it for 27 Celsius to 74 Celsius.
Because you have the preheating.
Yes, because we have the preheating. And then we just found the change in the temperature and divided by the initial, the change in energy divided by the initial energy. We found it to be 14%.
It might be, when you work on the next assignment, it might be good to also compare these numbers, which are great. Okay, by the way, you have to start with the purely theoretical analysis, but be useful to do a sanity check by looking at what others have done for realistic systems, for standard solar cookers or pasteurizers, because always there's an efficiency associated and losses associated with it, as you probably know. So
yeah.
Okay, perfect. Oh, let me do the polling before I forget. And okay, while that's going, one other thing also in your case, this is also a relatively simple sort of a system. Potentially you could experiment and hack something together, but again, you don't have to. But for the next assignment, you don't have to do it. It's just a suggestion. Okay, perfect. So while this is going on, let's have the last team, solar cooker team, who is going to present.
I will be presenting.
Okay. Daniela, okay, go ahead. Perfect. I think we're done with the poll. So let me just close it 1 second. Okay, you're on.
Good afternoon, everybody. We are the last team that will be presenting today. Our team name is Sun Box, and the team members are Kevin, Ikara, and Daniela. Today we'll be presenting some energy solutions to different problems that solar cookers tend to have. We're first gonna introduce some problems faced by solar cooking. We're gonna overview some existing products and solutions. We're gonna explore some innovations that improve accessibility and analyze implementation of innovation. Three main issues that we see with solar cookers are that they can be expensive, and this is a huge issue for undeveloped countries. Also, energy storage. It can be really hard to storage energy on a rainy or windy day. And also sun tracking. We'll talk more about sun tracking in the future slides. And another problem with solar cookers is ease in access. We want solar cookers to be portable, to have a temperature control and be safe to touch. And our main goal is that solar cookers are accessible for undeveloped countries. And we'll now discuss more issues and solutions that we are trying to achieve.
Hi. From this one, I'll be taking this slide. So our goal, our business goal is that for approaching towards the green art. So I'll be encouraging all the people or all kind of developing and developed country for both the solutions for both the country. So my problem is going to diverge into two ways, like one for the rural development people or the community solutions, and another part for the portable solutions for the developed country people who are love to go to hiking or campsite or anything, anywhere they can carry and can go for the easy cooking. So for the first solution, I'm going to the main problem that for the community people, it's basically upon the cost. Okay, so the cost and the accessibility and the perfect weather and climate conditions. So featuring on these some problems, I have proposed some solutions. Some of the parts are really there in the market, but it is not easily accessible as it was semi-automatic. So I'm going to introduce some ideas so that it can be fully automatic and it can be actually provide a solution to every kitchen. So here is the first solution for the rural community people. So that this approach can feed at least thousands of families. Our preliminary analysis shows that linear Fresnel reflectors that can use a thin segment of meters, and if we can structure this as a paraboloid dish, so that a large area that can actually focus the sunlight onto a fixed absorber located at the common focal point, and that can be actually capable of concentrating sun's energy approximately 30 times greater than the normal intensity. So this stage kind of Daniela, can you just showing the pointer over the algorithm flowchart? Yeah, over the, yes. I'm just talking about the parabolic concentrator. So now this thing has happened that this dish concentrates the solar energy approximately 30 times from its normal intensity, and this accomplished and accompanied with a dual axis solar tracker. So once it installed, and it will always focus to the sun. And for the solar tracker system, yes, that is readily available in the market. And three main key point of this solar tracker system is it is using a controller, it's using a sensor part of things, and it is actually the motor that can be moving throughout the to make the focus towards the sun. So this was the part of the solar concentrator and the solar tracking system. Now we are going to move that how the solar energy can be stored and can be used in the night or the cloudy ways. So I think of like if a steam boiler, we can use a steam instead of a solar energy. So how we convert the solar energy into steam? So we are putting a solar boiler over there at the top of the center of it, and these can increase the temperature up to 100 to 125 degrees Celsius. So, and this boiler is directly connected to a water supply. So as it is for a community of people, we can think of in a large scale. So water supply is connected to the solar boiler, and that thus with the help of the parabolic dish, we are going to able to boil this water, and the steam can be stored in a closed surface. So where we are going to store the steam, then it can be stored as a form of hot water. And there are 2-3 things we have to keep in mind, that as the pressure increases, then temperature will also increase. So if there is a relation, as we can see, is the basic relation is PV equals to nRT. So if volume is fixed here, so if the pressure increases, the temperature is also increases. So this is fine with the heating system, but we are also going to concern about the pressure for the safety purpose. So for the pressure, we have to control the pressure, and it is found in very much journal that a pressure kind of 1 bar is enough for the cooking. So we can actually control this with a valve. Excuse me. So And if the bulb is reaching to the threshold, then it will just release some of the water, and the pressure, sorry, the next slide, yeah. So the pressure can control like this way, and from that way we can extract the steam, and we can put it to the every houses, to the every kitchen supply. So what are the benefits? First of all, it's it's a large plant, so it will take some money, but it will have to invest some initial cost, as it has the low maintenance cost and it has a long-term project, and it gives some beautiful benefits. The beautiful benefits like steam storage that can be worked for the cloudy days or windy days, and kitchen atmosphere is much cooler, no passive gases were there, and as the pots are getting heat and getting, it doesn't require the direct heat, right? So it will give some comfort while cooking in the kitchen. And for the rural people, actually they have some less amount of space in the kitchen. And so keeping in this mind also that steam generates within 10 to 15 minutes, as we are very much familiar with it. So it gives me a automatic faster solutions for the rural people and the permanent solutions, because it will be constructed for a long term. So it can give a permanent solution for a rural people, for a long term person, and with a low maintenance cost. Although it's our preliminary analysis. And next slide, please. For the developing country, I'm going to present some crazy idea. It's my idea is like that. You are very much familiar with the tripod, like a camera holding, or everything like this way, camera or mobile capturing thing. So I kind of give an idea that why can't I use the tripod thing as a flexible, as it is. We are knowing that this is a very flexible thing. We can collapse. It can be collapsible, and it can be carried as we are moving out, or like this way. So I'm giving something to it that I took the idea from the sport cook from the Gosan, and I am just giving some innovations to it. So my first approach is that why it is not very much popular. It is a nice thing. Why it is not very much popular? So I thought that I'll be having something which will be useful for and which will serve the multiple purpose. So if you are going to carry this thing for the campsite or the outside, so you are going to think about the night sky, windy sky, and some of the necessary things we are going to carry, that mobile, iPad, or our laptop. So why can't we use some thermoelectric generator over there? So we are going to use the first stage, that there is a solar concentrator on top. Next is a vacuum tube, and it can be collapsible. So as the camp group is larger, we can enhance it based on our needs. So these kind of things are the two layer, and we are attaching a thermoelectric generator to it. So this thermoelectric generator will actually convert the heat energy to the electric energy. And if we are going to add some panel to it, like a port that can hold, that can charge a battery or the power bank, and as we know that power bank has a much easier to access those smart, our friendly tools like mobiles or like this thing. So I think it can be used as a multi-purpose thing. So basically the utility model is eco-friendly, portable, and having a thermoelectric generator. Also we can add 2-3 more panels of LED lights, so it can serve the purpose of our night camping also. And on the top of that, I am just improvising my idea to have a solar robot tracker, so it can always focuses the sun. And next, Kevin will actually go through the solar robot tracker. And Kevin, it's all yours.
All right, thank you. So as you can see here, we wanted for our solution to increase the utility of the solar cooker, and thus we decided to have the modular system. We decided to kind of increase the modularity of the system to kind of support making the cooker for either developing rural countries or developed countries for like common households that might want to adopt this system for using it in places with difficult access cooking, such as when they go camping and such. Thus, we decided to implement a solar tracker into the small form factor of the vacuum tube cooker that is accompanied by a solar collector, such as the Fresnel lens, as you can see in the figure 3 on the right there. This design combines both the small form factor of the Gosun cooker with the high efficiency of Fresnel lens and parabolic style solar collectors to help cook food incredibly quickly while maintaining a mobile form factor. We wanted to implement the Robo Tracker to increase the efficiency of the product and also help support the energy consumption that would be required by attaching additional utility devices such as the thermoelectric generator. And while previous solutions have tried to implement this implemented solar trackers, they are generally for larger, more industrial style solar collectors, which have larger collectors to gather more energy, and thus having more efficiency will multiply the effects on itself. But we wanted to bring that efficiency gain back to our small form factor to help support the energy consumption that we believe that our device will require. Okay, next slide, please. And that is the end of our analysis. Are there any questions?
Great. Good job staying on time and very interesting. Since we're basically out of time, I won't give too much questions, but I actually really like the fact that you considered the use cases carefully, which is the idea of whether it's going to be used in a developing world or whether in a developed world. And of course, these things will make a big difference in the technology. So that was really good. One quick comment on the solar boiler. It's an interesting idea, but keep in mind that the steam is a very corrosive material. So that means you have to be very careful with the choice of materials in terms of how you'll store it and transport it and so on. So something to keep in mind. And one other point about the costs. So the costs, you mentioned there's upfront cost, which is actually quite important, and it's valid for all the teams. There will always be I would say in most cases, there will be an upfront cost, and then there will be an operational cost. So when you think about this from a commercialization point of view, you have to somehow make the case that the upfront cost pays off over time, right? And people have a hard time making this case, right? For instance, for solar panels, you have to pay something upfront in order to justify putting that on. And there are various business innovations that came about to make this a reality. For example, Sunrun does a loan program, essentially. They lease the solar panels, so you don't have to do the upfront cost. So these are all interesting business models also for all of you as you think about this. Sometimes this choice of the business models can also affect the technology. So it's useful to think about these early on. But this will actually be part of your assignment 5, I believe. So anyway, you will think about this later on. But great, thank you. I think everybody did a fantastic job, and I was very excited to see everyone's presentations. And I'll see you all on Thursday. Great. Take care.
Polling
Any
for
questions?
our team. So polling for our team.
Oh, yes, I forgot. Yes, good point. Yeah, thank you. Yes, polling. So, yeah, so assignment 4 is you have about a month. So I expect a bit more detailed work. And I'll give more instructions at the end of this week. And keep in mind that the midterms are coming up in a couple of weeks as well. We'll be in between. And yeah, hopefully everyone's enjoying being home the next, or your dorms the next 2 weeks. And if you're able to, go vote in a month. Or now, I guess, you can mail in your ballot. So. Okay, very good. I think we have it. And thank you. And again, we'll have the office hours on Slack as usual tomorrow. So, but again, you can post your questions anytime you want. So great. Thank you very much. Take care. See you all on Thursday.
Thank you.